So we completed the modeling, analysis and design of our multi-story RCC office building according to the Nepal National Building Code up to our previous lecture. Today we are going to look at the design of mat or raft foundation in CSI SAFE software based on the reaction forces that we obtained from the ETABS model. Before beginning this lecture, I would like to request you all to subscribe to our channel in YouTube and press the bell icon. And if you find the channel and its videos informative, please do share our channel among your friends and encourage them to subscribe and help us support and grow. So there are two ways to design mat foundation in SAFE software. You can either begin from the SAFE itself and draw the plan areas, draw the grids, apply the loads in the SAFE software itself, or another method is to export the reaction forces from ETABS to SAFE, and we will design mat foundation today using the second method, that is by exporting the file from ETABS to SAFE. So for that, what we will do is your structure has to be modeled and analyzed to get the reaction forces. It is logged. This means our model is already analyzed. Then we will, I think our design is also complete here. So let's just do design here. Our building is being designed. And now after the completion of design, export it is a file that can be opened in our next software. For that, go to file, export, and story is SAFE v12 f2k file. Left click on this option. I want the story to export is our base where our mat foundation will be constructed. The loads to be exported are export floor loads and also the loads from above. Select the load cases. I will select all of these load cases except for these serviceability load cases, which I don't need for design. And I selected all other remaining load cases here and then click on OK. And also the load combinations, I will select all load combinations here and then click on OK, and then again left click on OK. Now choose a location to save your f2k file. I will create a new folder in my this training folder. I will hit save mat design, and I will save this multi-story RCC office building.f2k file in that folder. I will save it. You can look at below here, exporting model to SAFE. And now our export is complete. And also our work in ETABS is complete. I can close ETABS or I can minimize it. Then I have already opened the SAFE software here. So this SAFE software is also a product of CSI, Computers and Structures Inc. That means the same company that gave us SAP 2000 ETABS. This software is also developed by the same company. And this SAFE software is ideal for the design of substructure, mainly modeling and design of foundations such as mat foundations or isolated footings, combined footing with strap beam, and also for the analysis and design of our floor slabs. So the workflow in SAFE is similar to the workflow in ETABS. We have the same tabs at the top here, similar to what we had in ETABS: file, edit, view, define, draw, select, and all these tabs here. The workflow or the process or the steps through which we model, analyze, and design is also same as in ETABS. So let's begin with the design of our mat foundation. For that, first I will import the file that I exported from ETABS. I will go to file and then I will go to new model from existing file, or I will go to this import option here and I will import .f2k file. So left click on save.f2k file. Go to your folder where you had previously saved the F2K file, left click on this and then click on open. Now as you can see here, our grids have been imported into our software here. Also along with the grids, the loads that are coming onto our grids or onto our different points in this foundation have also been imported. Now we will proceed in the same way that we proceeded in ETABS. First we will go to define and then we will define materials. Let's see here, many different materials have already been defined here. So what I would like to do is, let's go to this mat 1 first and then modify show material. This is a concrete. So let's rename this as YUM25 concrete, since we are designing our structural elements using YUM25 concrete. And the material type is concrete. The material weight, the weight per unit volume will be, here is 0, you have to change this to 24.9926 kilonewton per meter cube. If you are not sure about the different values that you have to put here, because you have to edit the values in this material property data form. If you are not sure what value to put, just go to your ETABS model, go to define material properties, select this YUM25, modify show material, and use the same mechanical property data, these modulus of elasticity, Poisson's ratio, shear modulus, coefficient of thermal expansion, and this material weight and mass data from this ETABS property data form. So let's go back. Our weight per unit volume for YUM25 grade is 24.9926 kilonewton per meter cube. Our modulus of elasticity is 25,000 Newton per millimeter square. It's okay. Poisson's ratio is okay. Now coefficient of thermal expansion is 0.123450 and 5 per degree centigrade. Compressive strength is 25 Newton per millimeter square, and then click on OK. Now this CSAC30, this is also the concrete material. Again, I will just change the value here. Our weight per unit volume is 24.9926. We are changing the value of these values in material property data form because these materials are being used in our mat foundation, and we want the properties of these materials to be defined according to what we get during real test or according to the IS code. So we are changing the value here. Again, modulus of elasticity will be 25,000 Newton per mm square, and the coefficient of thermal expansion will be, this Poisson's ratio will be 0.2, and the coefficient of thermal expansion will be 0.50 and 5. Again, this is 25, concrete 25, and then click on OK. And finally, this we have a rebar material here. For this rebar material, let's rename this as FA500. The material type is rebar. The weight per unit volume of our rebar material will be 76.9729. You can get the value of this material property data form similar to what we did for concrete data in ETABS. Similarly, this uniaxial property data, the modulus of elasticity will be 200,000 MPa, and the minimum yield stress will be 500 Newton per mm square, and minimum tensile stress will be 545 Newton per mm square. Click on OK. Also change this rebar here, FE500 grade. This is rebar. Weight per unit volume will be 76.9729 kilonewton per meter cube. This will be 500 and this will be 545, and then click on OK. We have defined our materials and corrected for the material property data form, and again left click on OK. Save the model. Now you have to save a different model. We will save it as FDV file. In ETABS we saved it as EDV file. Now here will be FDV file, and let's say Raft design and save the file. Now after defining materials, we will define the slab properties for our mat foundation or raft foundation. Go to define slab property and then modify SOAP property here. Let's say rename this as mat. We will start with a depth of say 700 mm. Slab material will be M25. The type is mat for mat foundation. Thickness is 700, and this will be designed at thick plate, and then click on OK. Now there is one separate property that you have to define for design of mat foundation in SAFE software, and that is the stiff property. Stiff property means generally what happens is that in the connections of the columns and the slab, such as the column resting in the raft slab, in that point of connection the stiffness is extremely large compared to the normal stiffness of our column or normal stiffness of our slab. The stiffness is extremely large at those connections, and to model for those extremely large stiffness, we have to assign, first we have to define, and then we have to assign a stiff property at the point where the columns are resting on our raft slab. For that we will add new property here. Let's name this as stiff, and the depth of the stiff will also be same as the depth of our slab, 700. The slab material is M25. The type is stiff, and the thickness will be 700, and then click on OK, and again left click on OK. Save the model. Now after defining slab properties, we have to define the swale subgrade properties. For that, go to define and go to swale subgrade properties, and let's modify our this swale 1 property here. Let's call this swale support. Here what we have to indicate is we have to give the value of subgrade modulus for our swale. Since the swale does not take any tension, the swale fails in tension. This is for compression only, and generally the value of subgrade modulus is provided after the swale test is performed, and this value is indicated in swale test report. But we do not have any swale test report here, so let's see how to calculate the value of subgrade modulus. The subgrade modulus value is calculated if we have the bearing capacity. Let's suppose that our bearing capacity is 150 kN per meter square. First multiply it by factor of safety, which we generally take as 3. This is 450. Divide by the permissible settlement of our raft slab. Generally, this permissible settlement in case of different types of footing such as isolated footing or raft foundation is given by the standard codes. For now, we will be taking the value of permissible settlement as 50 mm. 50 mm when expressed in meter is 0.05. So divide by 0.05, you get 9,000. So 9,000 is our swale subgrade modulus. In kilonewton per meter cube, it is 9,000 kilonewton per meter cube, and then click on OK, and then click on OK. Then go to define again. Now we will define the load patterns here. Already different load patterns have been generated because we imported this model from ETABS. The load pattern have already been generated here. Click on OK. Now before defining load combination, let's go to this design option and then go to design preferences. Our design code is IS456, so change this to IS456 2000, and then left click on OK, and then go to define load combinations. So we want to define, or we want to add some default design combos. So let's add default design combos. We will add default design combos for strength and service, and then click on OK. all of these load combinations have been generated. So there are many load combinations here, so we do not want these all the different load combinations. So what we will do is we will delete these load combinations. Well, let's just click on cancel and go to define and load combinations. I will add one first combo for strength, and this strength combination is this 1 times dead load plus 1.5 times dead load, 1.5 times normal live load, and then 1.5 times storage live load. This is our strength combination, and click on OK. Now I will add another combination here for service or serviceability, which will be 1 times dead load, 1 times normal live load, and then again 1 times live load storage. This is our serviceability normal, and then click on OK. So these two load combinations are sufficient, and then click on OK. So our defining part is complete. Now we will go to draw option. First we will draw the slab of our raft or slab of our mat foundation. For that, choose this draw slab areas option either from this shortcut here or go to draw and draw slab areas. Now the property we will be using is slab mat 700. Now draw this along the boundary of our grid lines here. Click on enter. So this is our raft slab. Now what we will do is we will draw this okay, we have drawn the raft slab here. Now we will draw that stiff property at those places where our column is located. For that, choose this option here, draw quick areas around points. Our type of objective slab, the shape of object is rectangular, property is now stiff 700, and the dimension will be equal to the dimension of our column. Since we are using 600 mm by 600 mm column, I'm going to use 0.6 meter and 0.6 meter, and then click on these points here. We are drawing the stiff property at the location of our columns, at those points or at the connection between those columns and our raft slab to model for the large stiffnesses at those connections. Okay, now we have drawn the stiff. So this raft slab should extend along these outer edges of these columns also. So we have to expand our slab here. For that, just go to this select option here and select this slab by clicking somewhere at the center. If you click at the center, then all of these boundaries are selected here. Let's look here. You can see here 1 areas and 8 edges selected. But if you select somewhere near the edge, then only 1 edge will be selected, as indicated at this left bottom corner. So just go near the center and then click on this slab. Then all the edges will be selected, and go to edit areas, expand or shrink areas. Now since our column's dimension was 600 mm, half is 300 mm. So 300 mm, and then click on OK. The area have been expanded to the outer face of the column. So this is how you draw the raft slab and the stiff property. Now we have to assign the swell, which acts as a support to this raft slab. For that, just select everything here and go to assign support data swell properties. We defined our support data. Our swell subgrid is swell support. Click this and then click on OK. Now this swell support have been added here. If you don't want this to be displayed, check this set display option here and click on swell supports and click on OK. Now this won't be displayed. So now we have applied the swell support also. Now finally, before designing, what we have to do is we have to assign the design strips here, and that design strips will be assigned in both X and Y direction. For that, What we will do is we will go to edit, add or edit design strips, and add design strips. First we will add design strips in X direction, and strip layer is A here. Let's select the strip width as auto so that the program itself selects the width of those strips, and then click on OK. You can see these pink lines here, the design strips have been added. Again go to the same option, add design strips. Now select grid direction Y and strip layer B, and then click on OK. Now in the perpendicular direction also these strips have been added. So after adding the design strips, our modeling part is complete. Now we will go to analysis. First we will run the model and run analysis. So after running the analysis, we will go to this display option here and show deformed shape. We will look at the deformed shape for this service load combination and then apply. You can see that our deformed shape or our maximum deflection is 32 mm here. This deflection is, if you just zoom into this, the deflection is larger at these corners and minimum at the center. Since we took our permissible deflection to be 50 mm while finding the swell subgrade modulus, and our deflection maximum here is 32 mm, it's okay. So in this way you will check for deflection. Now you will check for swell pressure. For that, go to this display again and show reaction forces. We will see the reaction forces for again service load combination and apply. And the type of reaction you have to select is swell pressure, and it will be displayed as contours and deformed shape, and then click on apply. So you will see that the swell pressure is almost 300 kilonewton per meter square, and these swell pressures are again maximum near the edges. For example, if you zoom even further, exact value will come 281 here. Similarly, at the edges there is maximum swell pressure, but our safe bearing capacity is only 150 kilonewton per meter square. So one way to decrease the swell pressure will be to increase the area of this raft size. So what I will do is I will click OK here, or I will click close here. I will unlock the model. Then I will select this area and then again go to edit areas and expand or shrink areas. I will increase the offset by 500 mm. Remember, to increase this area there should be available space in your construction site, and you may not always have the benefit, or you may not always have the possibility of increasing the area. For now I am increasing the offset value by 500 mm, and then I will run the model again. Then I will go to display and then show reaction forces. For service load combination we are checking for swell pressure. Now you can see it is still 225 kilonewton per meter square. It is still greater than our safe bearing capacity. So let's unlock the model again. Now let's increase the depth of our slab. Maybe our depth is not sufficient. For that, go to define and slab properties. Change the depth of this mat 700 from mat 700 to mat 900. And if you change the depth of this mat slab, you also have to change the depth of this stiff property. Again stiff 900 and stiff 900 here. Click on OK, left click on OK again, save the model and run analysis again. Okay, now deflection is 14 mm, it is decreasing as we have increased the depth of our slab. Go to the display reaction forces again. There is a shortcut here. The load combination will be service and the type of reaction will be swell pressure. Apply. So it is still 210 kilonewton per meter square. So what I will now do is I will increase the depth of our mat foundation. Since it is our 8-story building, we may need to construct a larger mat to 1 meter. 1 meter here. Also stiff property, I will increase the depth to 1 meter or 1000 mm. 1 meter. I will select this slab by clicking at the center. I will go to edit areas, expand or shrink areas, and I will again increase the offset value by 500 and then click on OK. Then I will run the model again or run analysis again. So the deflection has decreased, and let's check for swell pressure now. These are the same, apply. Now our swell pressure has decreased to 165 mm or 165 kilonewton per meter square. So still it's not sufficient. Unlock the model, go to select this area, go to edit area, expand or shrink area. I will increase the offset value by 500 again, and then I will run the model again. Generally what happens is that if you perform the design of these mat slabs manually, then a smaller value of these areas and depth also may come to be sufficient. However, since this software uses the approach of finite element analysis, even if the deflection is exceeding or the safe bearing capacity is being exceeded at any point, then it will show failure. So now let's check the swell pressure again. Now it has decreased below 150. We have 136 kilonewton per meter square. You can see in this area there is large swell pressure here, and it's most probably because of the fact that we have lift core along this area. So now our foundation is safe in both deflection and in swell pressure. Now finally we have to check for punching shear. To check for punching shear, go to display and show punching shear design. So the punching shear, the demand capacity ratio for punching shear is being displayed here. You can look here, if this ratio value is less than 1, then it's okay, that is our structure is safe in punching shear. And you can see that the demand capacity ratio is not being displayed for our edge columns or for our edges here. It's NC here. It is because of the fact that we have shear walls, and these shear walls are acting as beams here, and wherever there is beam, then the shear wall or the punching shear check need not be performed. Also that will be the case for our combined footing with strap beam also. So the punching shear check is not being performed for these edge columns or at the edges here, and for the center it's okay. So in this way you can check for punching shear also. Now finally, when you have checked everything and it's okay, now you can go for rebar detailing. For that, what we will do is we will go to display and we will I think there is option here also.